Hi, everyone. Thanks for joining us for today's webinar Wednesday from GE Additive. My name is Mike Cloran, and I'm the moderator for today's session, which is on how to turn build failures into positive learning experiences. So before we begin, I just want to go over a few housekeeping items. If you'll take a look at your screen, you'll find multiple engagement tools that you can use. Now, all of these tools are resizable and movable, so just feel free to move them around to get the most out of your desktop space. You also have the option to expand the slides or maximize them to full screen by clicking the arrows in the top right corner. I also want to point out that there's a variety of help materials that are available in the resource list, and we encourage you to download any resources you might find helpful. Okay, now that I've gone through that, and we talked about how to make the most of your viewing experience, let's meet our presenter. And today we have Dave Bartosik, and he's the Advanced Lead Manufacturing Engineer at GE Additive. And Dave will be joining us in just a second to talk about this unique topic. But if you have any questions for Dave during today's webinar, you can use the Q&A section located on the right-hand side of your screen. And at the end of the presentation, we'll try to answer as many questions as we can. That's it for me. Dave, let's get going.
Sounds good. Good morning, good afternoon. My name is Dave Bartosik. I am lead additive manufacturing engineer here at GE, as Mike said. Today, I'm very excited to talk to you about build failures and how to use them to your advantage. I know that failures have a negative connotation. A lot of companies and people don't even like to talk about the failures that they have. I think it's good to put this up on the table and talk about it and figure out what we can learn from them. Personally, I've run builds, thousands of builds over my few years in additive. I think I've been with GE Additive for 4 years now and working in the additive industry for about 10. So it's a lot of EBM as well as DMLM-based systems. Unfortunately, I've not been exposed to the binder jet stuff quite yet. We've got it right here in-house across the hall from me, but I've just not joined their teams quite yet. So a lot of these discussions today are going to feel a little bit heavy on the laser and EBM side, but the mentality behind what we're doing certainly applies to binder jet as well. So throughout the presentation here, I just want to define what we're talking about in terms of failure and what the presentation will cover. Dive a little bit into process variables just to kind of set the stage for what we're talking about today. Root cause and analysis, documenting this is an extremely important thing. A few tools that we commonly use here on a daily basis. I know this is an entire study that you can graduate with from college, but we'll go into some brief, useful details there. Some common failures, kind of categorizing them based on where you see them and what their root causes are, how they can be tied together. A bunch of failure examples, and I've kind of interjected them between a lot of these different categories. That way it's easy to follow along. And then discussing about like knowledge handoff and how do, you've got all this great information, maybe you've done your root cause analysis, but what do you do with it? You've got it. You just throw it on the hard drive and forget about it. It's so diving into how to spread that information within your organization. And of course, at the end, we'll have a question and answers, as Mike said, so feel free throughout the presentation. If you've got something, we can always come back to certain slides. So if you need to reference that, you can definitely do that. According to the Merriam-Webster definition of failure, it is an abrupt cessation of normal functioning. And that is, I mean, if you think about it, you're printing your parts on a laser machine and your build stops. Absolutely. Like that, I mean, here we go. So like you've got all sorts of different issues that can cause that. Could be mechanical hardware within the machine. It could be your operator has done something incorrect in the build setup, or the both on the CAD side of build setup, or as well as the physical loading build platforms, loading powder aspect. You've got the environmental factors, kind of X factor as well. That's your not just power outages or compressed air, but also just where your machines are located. Are you in the proximity to train tracks or high elevation facilities? Software bugs, obviously we're not perfect, and nobody seems to be. We're running Windows, and those crash all the time as well. But you occasionally run into software bugs with this, both in third-party setup softwares as well as the actual machine HMI. And then just your build setup. I guess this also kind of falls under that user error, build setup from the operator perspective or your engineer designer perspective. Things that I'm not going to dive into in this conversation. I wanted to stay away from builds that complete normally, and maybe you have some minor issues, and it could be very geometry specific, parameter specific, as you're just kind of pushing that process window of that machine and material combination. Material properties and development, that's almost an expected failure. I do have a slide at this at the end, but essentially it's, I mean, you're planning on failure if you're running a new material and want to develop the parameters. Post-processing, we're not going to talk about. Same with design for AM and pre-computation modeling have been covered very thoroughly in other situations, and so I'm not going to use those much in here. That's they've got their own worlds to be discussed as well. So I guess I'm going to turn this back over to Mike for an initial question here.
Thanks, Dave. Yeah, so we want to...
what kind of failures others have seen.
Great, thanks, Dave. So we'd like to get your feedback on this, so select the answer that's most appropriate for you. So approximately what percentage of your builds have resulted in failure? Is it 0%, so none have, 1 to 25%, 26 to 50%, 51% to 75%, 76 to 99%, or 100%? Please help me. So again, is your percentage of build failures, is it 0%, you're perfect, 1 to 25%, 26 to 50%, 51 to 75%, 76 to 99%, or everything you do is a build failure? So we know that it's an estimate, so just pick the one that you think best suits you. And let's take a look at the results. And Dave, let's get your impression of this. So almost between 1 and 25%. So people have 60% of the people said, maybe upwards of 1/4 of their builds are come out as failures. And then you got 1.9% have had 0 failures. So is this about how your experience, Dave, or do you have any comments on this?
Yeah, so this is somewhat of an interesting question because we don't have the prerequisite of what industry or role is your company playing in additive. Are you a small rapid prototyping shop and you're running one-off builds, something different every day, or are you in high volume production? So this, I suppose, is a little bit skewed. I'm going to hope that a lot of our customers are running in the low rate, high volume production with that 1 to 25. That's great. That's looking good. 0%, you either don't have machines or might be exaggerating is my, I'm going to joke with you on that one. But the folks down in the 100%, we'd be glad to help you. Our AdWorks team, not only myself have experienced build failures, but everybody here. I'm actually really surprised with the 1 to 25. I thought we would have a group that was more in the 25 or 26 to 50 kind of range. So this is better results than I anticipated. Very curious to see this. I like this. Mike, if you don't have any other comments, I suppose I can keep trekking on.
Yep, you can continue.
Okay, diving into process variables. There are a lot of them, and you have to understand them very responsibly. This is one of my favorite fishbone diagrams. This is just a handful of variables that apply to the laser powder bed manufacturer. So the DMLM, laser powder bed. Very similar for electron beam, binder jet. Some of these categories totally, especially in material and process, it's just a different modality. But essentially what we're diving into here is trying to look at what are all of the different aspects that can have an effect on the cost, time, and quality of your parts. That's kind of the age-old saying that people use when it comes to buying a lot of things is you've got cost, time, and quality, and you can pick two. Or, if cars, for example, if you're buying aftermarket parts, it's performance, price, or reliability. It kind of goes across the field, but I don't I think that's cutting it a little bit short. I think there's some sliders that you are always trading off, and maybe you can have some faster parts with good quality still, but you take a hit on the cost of those parts. And so it's always this balancing act of where do you want to end up and what's the customer expectation. This is an excellent troubleshooting tool when you are having a build failure and looking for that root cause and working backwards of, you know it has to do with your recoder jammed, but why? What are the different factors that play into that coder jamming? Is it your CAD setup? Is it your mechanically something going wrong? And so just a great tool. This is a fun chart that we like to use, but kind of setting the stage for there's a lot of things that can affect your end parts. Transitioning that right into root cause analysis and capturing the data. One of my sayings that I like to have with technicians things here, it's absolutely okay to make mistakes, but it is unacceptable to not learn from that mistake. Even repeat mistakes, that's fine, but we want to make sure that we don't just find a mistake and ignore it completely. And typically we'll use, these are kind of the common ones we like to use to explore both root cause analysis as well as preventing failure modes. So we've got Pareto charts. Fantastic. This is, very common. Really helps you categorize and organize your failures in a order that shows the most frequently happening and gives you priority. What do I want to fix first? So just kind of an example chart here. There's not any real data in this one, unfortunately, but that one on the far left there is happening the most frequently and causing you the most, whatever it may be, downtime or build crashes or non-conforming parts. And so that's probably your first target. It also gets compound. You can add in the cost of each of these variables into and kind of give them a weight. Fishbone diagrams, just saw that on the last one. Excellent cause and effect and helps you work backwards to track down where your variation and defects may be coming from. You can check them off one by one. Maybe you've got a circled group of you're not quite sure which one it is, and go through each variable and isolate it, verify it does or does not contribute to your issue, and move on. A lot of failures are compounded by multiple issues, and that's where it gets kind of tricky, but absolutely valuable. 5 whys is nice and simple. I know the automotive industry likes this. I got pushed a lot with this when I was working at Honda to use 5 whys in troubleshooting. It focuses more on what is the root cause and not just what are the problems you're having or the symptoms. And often these split into multiple. You'll get to one of the second or third whys, and all of a sudden you've got multiple root causes kind of defined and corrective actions to make from there, which I have an awesome example on the next slide. FMEAs absolutely require this when you're going into production with parts. You're going to need this in your operation and production qualification. And it's trying to map out all of the different failures that could happen and what are your mitigation methods to make sure that they don't happen. What have you put in place as planning to prevent failure? This is often a continuous improvement document that as you can think of everything you want and there will still be something that pops up and you end up editing that in the future. So the example I was discussing, just recently on LinkedIn, there was a fun survey of, they have this build failure in this article called Why the Fail. And they're putting out some build failures and what happened and then having some fun with, guessing at speculation. Why would this have happened? And in this situation, they've got this part over here. In the XY plane, there was kind of a big sheet body just right through the middle of the part. That's not supposed to be there. Those holes are supposed to flow through. And it was all closed off. Powder was trapped in there. And they had a lot of fun with a lot of people wanting to say, was the STL, was it a bad STL file, bad CAD file? Did something happen in the slicing because of that? And then finally revealed, no, actually it was because the build had stopped. And so going through the YYYs here, you've got, at about 20 millimeters into the part, suddenly layer 0 was scanned instead of that layer 20.05 or whatever they may have been at. And so, well, why did layer 0 just suddenly scan? Well, operator had restarted the build at layer 0. Like, well, why did that happen? You know, the build had stopped, so they weren't to restart the machine, didn't change the current layer height. And it's like, well, why did the build stop? There was a power loss. And so there was this big justification for, this is a great reason why you should have a UPS, battery backup, uninterrupted power supply, or battery backup on your machine. And that's true to some degree, but I think there was a huge takeaway from this that was missed at the operator restarted the build at layer 0. And to be fair, the little video on this was about 10 minutes long. They may not have gone into every little detail, but the restart procedures, why is a build restart should never, unless you've failed at layer 0, should not be started again at layer 0. And we're the checklist to help the operator through this and make sure, you know, did you look at the log file? When did the build stop? Now set your next layer to that active layer. And the training that goes with that, but not just training on how to use those restart checklists, but the bigger one is how to report your non-conformances to your quality department. This needs to be plugged into the router. Finding this mistake post-build would certainly not be a good thing to have found. And so again, I want to give absolute fairness that just they may not have dove into these subjects throughout their video and analysis of this, but it's always one of those, you don't just do your 5 whys and come up with one thing. And UPS, yeah, okay, but it's not perfect. And also, training and checklists are essentially free in terms of actually purchasing something. You have to spend the time and invest into it. But okay, next we're going to talk about some common failures, things that we see very frequently, whether it be actually ourselves here at GE or customer sites, or just even the additive industry in general. First one, it's kind of the weird one, environmental and facility issues. You can have utility outages. This is very frustrating for some customers, depending where they are and how the infrastructure of their city is laid out. And other ones don't seem to have an issue with it. But it also not only applies to electric, but your air compressors, or maybe you're just taking some sections of the facility down for maintenance. I think the two effects you get from this are either your build hard stop, where you've completely shut out power. It's been out for hours. You're beyond the restart window time, and you have to completely start over. And then there's those soft stops, where maybe you had a brownout or the power went out just momentarily. You can reboot your machine, or even if you're very proactive and have your UPS, fire back up where you resumed and get that build rolling again. There's a few different measures you can take to prevent that for each different type of failure mode. And temperature variation, I've seen this personally in a shop that we're setting up as a temporary shop. It was just us internal, using a small site. We actually didn't have, the building we were using did not have any heating, air conditioning, anything like that. It had a heater, I suppose, but no air conditioning, middle of summer. And it would easily get up to 85 degrees within the building during the day. And the machine ran great from morning until about 5 p.m. And the increased temperatures caused our chiller to work harder than it was intended to. They're designed to be in an air-conditioned environment. And the chiller would trip out high-pressure alarms and stop the build. And it usually happens, it's kind of frustrating how it would happen after you had gone home for the day and everything looks like it's running smooth. So temperature controls are absolutely critical to keeping these machines running. And that's also covered in the installation manual for all the machines. So it's, that was us kind of pushing the process limits. Humidity has definitely more of an effect on powder than much else. The machines happen, they're inert with gas or under vacuum. I'm not sure how this plays into binder jet. I could ask some of the guys on that team, but humidity will absolutely change the flowability of your powder. And as you increase humidity, I suppose it gets a little more sticky. As you decrease it, depending on what powders, materials, and particle size you're running, it can actually increase your the dangers with the powder and have a much higher risk of explosion due to static and arcing. Atmospheric pressure, I think we talked about this a little bit earlier, but it's being at sea level versus up in the mountains of Colorado. There's absolutely a pressure difference. This is not applying to weather patterns coming in, stormy one day and sunny the next. That's, I think, a much smaller scale pressure difference. But in these larger altitude changes, the pumps will perform differently. The cooling of the machine as well, where we've got a lot of heat being input with multiple lasers of multiple kilowatt lasers or an electron gun, and you're trying to keep the machine in a nice steady state temperature. The air conditioning units for these machines will perform differently. They'll be cycling on and off more often. The heat doesn't dissipate as well in those inner airs. EMF changes, this 100% applies to EBM. I don't think there's much unless you hit some pretty extreme cases for laser or binder jet, but we're using electromagnets to steer the electron beam. So any kind of changes in your fields around you is absolutely going to affect that. This could be heavy equipment that you're moving around or toolboxes. We've done a fun study with put the bead right in the middle of the plate, get it to about 100 microns in size, very low power, just enough we can see it with the camera, and push a toolbox past the machine right in front of the door there, the process window. And you can watch the beam move a couple hundred microns to one side and swell up into a nice out of round shape. And then as the toolbox moves away, the fields kind of return back to normal and you're back to your centered spot. So that happening during a build, I actually have a slide on the next slide I believe is about that. So we'll go into that a little bit more. Vibration, locally on your site, if you've got large heavy equipment, this kind of varies building to building. Here in Cincinnati where we've got these machines, we don't have some large post-processing shop. It depends on what the application is, right? We might have cranes and forklifts driving around all day. The vibration is absolutely going to be an issue. Here, we're not really worried about what you see. Most of our customers also don't have to worry about this. Or it's just even proximity to heavy equipment. If your building is backed up to some train tracks and you've got large locomotives going by a couple times a day, that vibration could absolutely mess with your beam quality or powder bed dynamics for sure. EMF experience, yes. So beautiful customer site here. 5 Arcane machines in a row. They're in the back corner of the shop. This shop happened to have a bunch of CNC equipment, so they're turning large 3-phase motors on and off. There's a bunch of EMF in the rest of the shop. They've got it marked out very clearly. Nothing massive or anything unrelated to EBM comes within the larger boundary in front of the machines. Then they've got one that's even closer, and that is no toolboxes, no cell phones, trying to really minimize it. And awesome setup, and they were finding that these build anomalies would show up, and it started to become a regular basis, and they discovered it was on Wednesdays. They would get the beam in that lower picture there you can see has shifted the XY position of this. What's going on? I went, well, Wednesday's trash day. On the opposite side of this wall, there are dumpsters for an adjacent business, and the trash truck would be pulling up and dumping and sitting there for a while, and this big block of iron with hydraulics is just running up and down and lifting dumpsters with who knows what. And so it was just a huge aha moment of, well, yeah, I guess either we don't run builds on Wednesdays or we need to work on, can we talk to our neighbors and see if we can have that changed. But another EMF interference story was that there was an HVAC unit directly above one of, not necessarily this site, but a customer that had a lower ceiling than this, and the HVAC was right above it, and every time that unit would kick on or off, it would also disrupt those magnetic fields and shift their calibration. This is covered in both pre-installation guide and a pre-site installation checkup that an FSE shows up and runs around with an EMF meter. Finding the garbage truck, unless the FSE was there on a Wednesday, we probably wouldn't have found that. So not necessarily a bulletproof system, but at least there's checks in place to make sure this doesn't happen beforehand. Utility, talked about this. UPS, backup generator, is kind of your top tier. UPS, because even with the diesel generator, it takes time to fire up. So if you've got power loss, you don't get instant power. That UPS keeps you at your 400 volts, and then the generator kicks in and can sustain you as long as you need. At minimum, a little UPS on the computer is great. That helps you maintain your current layer height. Yes, your PLC will kick all kinds of errors out and say that there's no power, the chiller's not running, the compressed air may be not flowing because all those solenoids have shut, but you've got your log file still running and your machine up and running, at least where you were at, not losing your place. Compressed air, I've seen, a lot of sites do this with backup compressors just as standard surge tanks. What I've done in the past, that same building I was talking about earlier with we were just there temporarily, let's run for a couple months and then we'll be out of here with a couple small machines. We were able to run just a small Lowe's Home Depot air compressor. little tiny thing that's just enough to keep the machine running. It was tied into a check valve, so the main air compressor we had running outside was fine, but occasionally it would run out of diesel fuel or whatever may happen with the shutdown on the weekends. And so these little compressors would then kick in and just keep us sustained as long as it could. Same thing with processed gases. This little picture here. It couldn't unfortunately show the entire part, but basically while printing these vertically, the nitrogen at the facility had run dry. Our supplier hadn't showed up that day to drop off more nitrogen or whatever it may be, but the machine's inert. It's continuously cycling its gas through the process chamber, the filters back in. But as the oxygen levels began to increase, we got these nice little oxidation yellow colors starting to show up in the parts. And the build actually finished. It stayed within the process limits of printing, but definitely a defect here. I'm sure the material properties on that are subpar. And we've got another poll question for you guys, keeping you awake.
Yep. Thanks, Dave. Okay, for our next poll question, get your feedback on how frequently do you experience utility or facility failures that affect printing? Is it very frequently, as in several times per month, frequently about once a month, occasionally a few times per year, rarely about maybe once per year? You've never had facility problems, you have excellent countermeasures in place, or you've just been simply very lucky. So again, how frequently do you experience utility or facility failures that affect printing? Very frequently, several times per month, frequently about once per month, occasionally, maybe a few times per year, rarely, about once per year, never because you have the countermeasures in place like EPS system or something, or never, but you've just been really lucky. All right, I'll give you a second to respond. Let's see how this comes out. So, looks like most people said, about 40% said a few times per year. And anybody who's had build failures, they know how frustrating it is even a few times per year to have that happen. And then the next was rarely, maybe once a year. And good to see that 8.2% have excellent countermeasures in place. So Dave, what are your thoughts?
Yeah, this is great. Pretty much on par with what I expected to see here. The very frequently, I feel your pain. We've recently moved to a new facility here in Cincinnati, and for the first few months, it was several times a month, absolutely. Not necessarily weather patterns or anything like that, but it was always, we've got new machines and to install these, it's very sequenced the way that things were coming into the building, and it would shut down bus ducts and then install new machines and then fire them back up. And so anything that was running had to be very carefully scheduled to make sure we weren't shutting things down mid-build. The occasionally a few times a year is what we see most places. Once a year, that's awesome. I would be thrilled with that. I know when we were at some of other sites with anywhere from 10 to 40 metal additive machines, the few times a year would happen. Not necessarily always. It was usually electrical. Compressed air, processed gases, we had that locked down quite well, but the electrical sometimes was natural disaster. Sometimes it was a pickup truck that slammed into a power pole and shut us down for an afternoon. It's kind of a painful thing when everything's running smooth, you're happy you've got machines running, and the entire site shuts down and the emergency lights kick on, and you're just kind of looking at each other like, well, as soon as it comes back on, we're going to rush to get these started. And after a few minutes of, you've exceeded your maximum time that you allow within your process specs to restart a build, you just kind of go, well, guess we're going home for the night, and we'll fix this tomorrow, if it's back on tomorrow. The excellent countermeasures, that's great. Countermeasures are absolutely possible, and they are just expensive, which is why we don't see more of that. It's especially the UPS that's facility enabled rather than just small UPSs on the machines. And the lucky, good for you. I'm envious. Okay, process gaps with operator mistakes. This is probably the most common at least with new customers. Having detailed work instructions and training and eliminating that human error is, it takes practice. It's just using the user manual or the training that you had maybe 6 months ago isn't always the best option, and leaves room for errors. So really making your work instructions clear and concise. I mean, the user manual for these is hundreds of pages long. If you want a work instruction for how to prep your build, you want a couple pages at most, and it's very specific instructions. Pictures help absolutely as well. Training, what I see a lot is we have a lot of customers that are getting into additive that are new, and they send some of their higher level engineers or management to training and learn how the machine works. And then the machine is delivered, and they help out with, they hire some operators and technicians and kind of play the game of telephone if they explain what the procedures are to these operators. And then we're finding that there's often some gaps within that. And so having everyone that interacts with the machine trained is extremely helpful, as well as keeping that up to date. There's always updates to the machines, whether it's hardware or software, and ensuring that everyone is also caught up to date with whatever those changes may be. Human error, very difficult to get rid of. Typos, fat fingering, just general oversight is, it varies very subjectively person to person. Found that if you find those people that are extremely high attention to detail, it happens less. So it's part of the hiring process, I suppose, and deciding who works with your machines. Pencil whipping, we see this a lot with too many checks. You want to check the weight of the powder. You want to check the flatness of your recoder blade, the flatness of your build plate, the surface roughness of your build plate, the chemistry. Chemistry of your powder is kind of, that's not necessarily right before you start printing, but so many checks in a row that very quickly becomes complacent to just check them off. It's always fine. I never see issues. And that's where you run into problems where issues may drift into the picture without being captured. So it's, capture the important data, but allow the log files in the machine and other processes to help you with that. And then accepting good enough. This is tricky when you're in a rushed situation. We've got to get this Friday afternoon, get that build running. You're throwing a start plate in there, leveling the blade to it. It might be close, but adjustments take time, and measurements are, a very attention to detail, taking the time on it, and it just doesn't always, maybe the last build ran great, and the build plate was 50 microns out, so it'll be fine with this one. And maybe this part has way more internal stresses, and it'll rip itself right off the plate. So there's very give and take with this. Sometimes you get lucky with accepting good enough, and sometimes it kills your builds. But the biggest takeaway from this is just enforcing compliance. You've got your work instructions. You've got what your training matrix is, and is it up to date? And this is aviation folks and medical folks are just laughing. It's like, yes, of course, this is exactly what you have to do is follow what you've set in place, and simple as that. So, got a fun situation. This actually was with our binder jet folks. Contaminating powder. So this is a small screenshot of, we'll say the entire binder jet process and do a little fishbone here. But there's the powder conveyance and refilling. I'm not even exactly sure how this happens, but essentially there is a hopper of powder that's where it's loaded from. When it's fresh powder, virgin material out of the containers from the manufacturer, we load it in here, and it goes through some system. I'm not sure if it sieves or if it compacts it into the build box or what they're doing, but there was not any powder flowing from the container. So you very quickly dive into these, okay, why is it not flowing? Initially there's the design stuff, right? We've verified all of these through design before the hopper was even acquired or manufactured. Is it big enough to hold the powder you need? Is the slope appropriate so that the powder we put in it is actually going to flow out the funnel at the bottom? With both new and used powder, does all that work? Yes, that's cleared, tested, ready to go. Okay, so what's the engineer looking to next? Like, well, is there even powder? Is it not flowing because there's not any in there? Well, okay, we'll look into that. Is the vent on top? Is it opening, allowing powder to come through? Does the valve at the bottom, open and close. Yep, okay, is there something else in there? And very quickly, we found there was something else in there, and it was a desiccant bag. This is what the powder is often shipped with to keep it dry from humidity during shipping and things like that. And so while kind of happened in an unfortunate way of not finding the bag entirely intact, of sticking a tool up through the bottom of the hopper to kind of poke around and see, is there some kind of obstruction? And these little white, clear silica gel packet things kind of started pouring out. And then some powder came out, and then we closed the valve and opened the top and found there was some desiccant bag in there. Only one. Every bottle comes with it, so it was just one of those operator oversights of not necessarily looking at exactly what they're doing, but you've got to prevent that. I mean, what if, you look away for 1 second and the desiccant goes in there and the build has stopped because powder's not able to get into the machine. Controls for both how you're using it, but also, can we talk to the supplier? Hey, do we really need desiccant bags inside the bottles? Can we have them in the shipping containers instead? A secondary container that all the bottles are in, and that has a desiccant. Just one of those quick foresight things that can really catch you off guard if you're not paying attention. Build failures during setup. This is kind of dives into the area I didn't want to talk about too much because it's been covered very well in other discussions. But the stress management of parts, how you're adding your supports, orientation and platform location very much falls under design for additive manufacturing. Making sure your parts aren't touching. I've done it. Everybody does every now and then. You're looking at it in CAD and it looks close, and I forgot to use the collision detection tool, and ended up with 2 parts welded together. Slicing, if you just don't use the right settings, the wrong layer thickness, there's usually some controls built into the machines that prevent you from doing this, but not always idiot-proof. Combining jobs is a risky move. It's great when you're in time crunch if you know your parts from 2 different customer jobs, or 2 different, maybe you have the same customer, but 2 different orders. If you know they're going to print perfect, you've run them before or something like that, great. You can throw them together. Probably won't hurt. Make sure you've got enough powder and the dosing is modified to accommodate that. But it's a higher risk in the sense of if one of them fails, you lose them both. And occasionally you can get away with deleting one part from the build and resuming the other one, which can result in build lines, and then you have to explain to each customer why their part may have been affected by somebody else's, and it's a risk-benefit trade-off. And then the amount of powder that you are demanding for the job and how much your dosing is set up for the machine. A lot of this is set up offline and then transferred to the machine. The technician doesn't know what dosing should or should not be. The machine has some functionality built in to at least say, hey, you've got enough loaded, but it doesn't look at how much scan area you have. If you have a very thick, dense part with a lot of consolidated material, you're going to need a higher dose factor, and if the machine doesn't, at least at the time, doesn't calculate that for you. So I think I've got an example on that next. Yeah, several examples. So this top picture is a little bit difficult to see, and the recoder is essentially heading out of the screen towards you. And this is the very furthest edge of the part, the last bit that gets covered by powder. And it was just in the last few layers that it started short feeding. And most of that's due to the transition from, it's much thinner as you go down the part. And the very top, it's this big, thick, bulky flange. Did okay for a little bit and then started short feeding. And unfortunately, luckily, this one, we were, I think, able to, there was stock ads on there, so we're still able to use the part. But can also happen right in the middle of a build. And then it can also be covered up. Maybe it's thin at the bottom, thick in the middle, and thin at the top, and you've got this lack of fusion, porosity, delamination going on in the middle of your part, and you might not see it until the build's done, which unfortunately is sit there and realize how much time you may have wasted continuing that build. The 2 on the bottom there, Arcam ones, these are both builds have run. The one on the right is actually very similar to the previous one we were talking about, where it's just very dense, bulky parts. There's 3 cubes right through the center. They're all in a line, so if all of a sudden you go to supports for a few layers and then you start melting bulk parts and they're all in a line like that, you're absorbing all of your powder that you're trying to distribute. Whereas if they were in a diagonal line across there, you'd take a little bit from the back of the build, some from the middle and some from the front, and end up not short feeding at all, but perfectly putting them in a line. The first two that the recoder hits are taking all of the powder, and the middle one gets left behind. The bottom left one there is actually I don't know if anyone's seen our tree that we did for the zoo. This was one of the trials that we ran out of powder. Hadn't skimping by with some powder that we had, thought we had enough, pretty close. We turned off the powder sensors because we knew we would be close, or turned off, the powder sensors were still active, but the build would not stop if it sensed zero powder. So 0 powder pulses were happening. We came in the morning. Yep, you open the window, you look in there, and you see this huge void, lack of powder. Essentially, it is attempting to spread powder, and none is being spread. And so it lowers the table, scans again, and you get further and further out of focus. There's preventive measures to correct you from making these mistakes. In EBM, we've got the powder sensors and the feedback loop, and default, it's turned on that if you have a certain number of 0 pulses, it says, hey, you're out of powder, and it stops your build. It prevents you from doing what this tree has done here. And then the little clip art on the left there is similar to what we get with, I couldn't find a good enough picture quickly, but we've got QM coat in the laser machines, and it's looking at that trailing edge, the last edge of the powder bed that gets covered, and ensuring that you have sufficiently covered it. And if you have thick parts and it's sucked up a lot of that powder, it will actually sense, hey, you've got a huge percentage error. You're missing powder from a big chunk of your left side here. We're going to coat again and just make sure everything's covered. So using the tools is excellent. Turning them off, maybe you save a few seconds per layer with taking camera or taking pictures, but they exist. I'm not sure what there is for binder jet. I know there is what they've been calling short spreading is a function. Do not know if there's any kind of sensing on that or not, but sure, again, the binder jet folks would love to discuss that with anyone curious. Software, this is inconsistent at best. It's hard to find a lot of repeatable errors with software sometimes. So file transfers, just copy and pasting. I'm sure you've all experienced it with maybe images. Seem to be pretty frequent that when you copy from one network drive to another or onto a flash drive, it kind of corrupts it and you end up with just half your picture missing or jumbled. Renaming files and having them properly named or using the wrong file that has a similar name. Same thing with slicing. I've had a weird thing where slicing parts and saving the slice file directly to a USB drive instead of locally seemed to put a big sheet body through the part. Just like that picture of that Why the Fail article in the LinkedIn that we discussed earlier. It just out of the blue. So sliced it again, saved it locally, and no sheet body in the parts. There's interesting things that computers do. I mean, it's difficult to fix all of these because there's not necessarily always the reason. Now, bugs and crashes within the HMI and machine software, absolutely. That's where we have complete control, and we can go in and there are known issues that we're fixing for customers, and not everybody runs into them based on how they're using the machines. But there's also the silly stuff, the touch screens, right? It's a lot of times we'll have people pointing at something on the screen and touch something, and all of a sudden, you know, they're prepping the machine and somebody comes up to point at what's this button do, and it moves the recoder, and you got to start over with your scratch code maybe, but it's happened. User installed programs, another tricky one to really dive into. Like, is my machine acting up because I've installed, you know, I've got wireless keyboards now in mine. It's great. I can sit back and relax while I'm working on it, or I've added a bunch of these webcams that we've tied into some internet program that we can observe the build from anywhere in the world, and there's give and take with that. Sometimes it goes totally unaffected, and sometimes it can throw your machine for a loop, so it's something to be very careful and tread lightly. And vectorization. Super complex parts, you may run into long calculation times of what are the vectors that it needs to scan. Luckily, we now have pre-vectorization, so we can calculate all that offline on some other computer. The main issue you run into there is just a long layer time. The scanning will be done, and it will just be sitting there seemingly idle, and it's just waiting to calculate the next layer. Hardware, oh gosh, okay, we're running short on time, so I'm going to start powering through these because these are overusing consumables. I've been very guilty of this, especially when you need to be cost conscious. Reusing coder blades with the hard ones, as long as it's in good shape, you're fine. The soft ones, a lot of times little nicks and defects that you don't see with the naked or the bare eye are not necessarily, they're not always perfect. Heat shields in RCAM, you'll build up that metallization and it looks thin, and on the next build it's flaked off and fallen in your build, and you've got some voids or contamination. Filters, you can use them and it'll usually pop you a, hey, your filter is reaching its maximum differential pressure, you should change it. You can start another build that's short and hope you don't breach that differential pressure again, but your pumps are going to be working harder, you're pumping more heat into your system, and that can change your material properties. Alternate sourcing, as long as you're following whatever the manufacturer's specs are, that's great. Sometimes you don't know what those are. With the RCAM heat shields, for example, it's not just stainless steel sheet metal. They are pickled, is what the Swedes call it, but it's some kind of an etching or coating that's on these heat shields to help the metallization stick to them better. And if you were just to go have your local mom and pop shop laser cut you some stainless steel, it probably wouldn't hold half as much metallization because of that process added to it. So it's, if you know it's there and you can follow the same pickling process, fantastic. But it's something to be careful of, and a lot of new additive customers want to try and save money on sourcing their own parts or consumables for the machine. Keep an eye on laser power. They all degrade over time to slow degradation. Make sure you're regularly using your power meter and checking that. Keeping cover glass clean. That kind of falls under work instructions, checking those. And sensors, maybe it's a loose wire or you're out of calibration, and always staying on top of the critical process sensors is helpful, especially in production situations. Real quick, easy hardware fixes that we've run into. This is the door, the process chamber door, this big one on the right side here. It's kind of a push to open. It's like those cabinets that don't have a handle. And when it opens, the build stops. It's a secondary safety measure. The laser glass is actually the smaller window behind it. But we had a tour group come in and, look in this build here, and they're poking their head in there looking at it. And one guy leaned too hard and popped the door open. The build stops, and it's, we have technicians there. It's fine. They were able to resume the build and get things going. But it's like, well, what can we do? There's an interlock. It's not an actual locking interlock. It's just the magnetic sensor that's on there. And, could we remove that? What's the safety that comes? What's this door here for? Diving into that. Detailed safety risk assessment required. That's kind of the more dangerous route, I'd say. But option 2 is just this plunger. How hard do you have to push this door to pop it open? We'll just make it a little bit harder enough that when you lean on it, it doesn't pop open. And easy peasy. Same with RCAM doors. This probably happened just because we've moved the machine a few times, but the back door on the back of the machine had a little bit of play in it. The latches, you would latch it and it would hold the door closed, but not necessarily securely closed. Enough that when a technician was working behind the machine, he just kind of bent over and bumped the door, and it killed the build instantly. Starts beeping, he freaks out, everything's fine, wasn't an important build, but real quickly, we just open up the back door. These latches have some tension adjustment on them. It's much more snug now, and it's kind of become part of our installation qualification checklist of, hey, let's make sure all the doors, if you bump into them, cannot trigger the interlocks. Recoder access resistance. This happens in absolutely, I know I've experienced in both RCAM and laser. You've got bearings and a motor driving this recoder back and forth, and you want the bearings get dirt and debris. You've got a lot of metal powder and a lot of different things going on in this process, and keeping them clean and greased properly is very important. So whether this was lack of PM or maybe something wasn't tensioned properly, these graphs are a little bit busy to look at, but essentially what we've got, the red is the velocity of it. So 0 is kind of through the middle of the graph there, and it accelerates upwards as it's dragging powder across, retrieving powder from the dosing module, slows down very slowly, applies it over the parts, and then it speeds up and dumps the rest in the collector and then flies backwards to the side where it rests during the scanning. Huge spikes when it's moving to the left on this lower graph here. And so they're basically killing the build because the torque is too high on this motor. So you quickly dive into these, where can I start fixing these bearings and what's going on here? And then, like I was talking about before, development failure, you just have to expect it. You're running, these are nice little porosity samples, and I think all of these probably printed, each one of these with slightly different laser powers, scan speed, spacing, little micrographs here. This first one's beautiful, but these ones down here in the bottom right, I'm sure that they, they might have been scraping away bits and pieces into the build while it was running. You just have to expect this. Pushing the machine to its limits, you're running maximum laser power. You're going to have a lot more heat soak into your parts, and making sure that you can handle that with the cooling on the machine. New geometry, things like that, island builds, you almost expect it like, hey, we're trying to push these supports to the limit. We really need as few supports as possible. You almost expect you're right on that teetering edge of buildable or not.
Hey, Dave. In the interest of time, just so we have time for questions, I think we're going to go ahead and skip this poll question, if that's okay with you.
Yep, 100%.
Okay.
Knowledge transfer. This is huge, and so you've got all these failures. You've captured them, but you cannot just squirrel it away. There's some degree of that within your organization, your company, of IP. If things are discovered, great, but presenting to the broader audience of who is using your machine and in what situations. We personally do tech talks internal. We don't really actually do lunch and learns anymore, but similar things. Maybe you've got your specialized task force. If you've got a group of people that when there's a build failure, they come in and really help you run through this RCA and then spread that information of what they've discovered to the rest of the organization. They could be the people who've run additive the longest. They could be your Six Sigma black belt folks, all over the place with how to get this information out. Keeping that data accessible. In the old days, we would just print it out. We had this cool binder of build failures, and you would flip through the binder, and usually when you were the new hire, part of your day was like, hey, go flip through the binder and just look at different things that have happened. And just seeing what the failure was, and then when you see something similar or something close to it, you can go reference that binder again. Now, got much more advanced tools, online kind of Wikipedia, internal Confluence, things like that. Awesome, but you have to capture all the data. If you just have a brief sentence and kind of some jargon about what maybe happened, it's not enough. You want to tell that whole story, that you leave the company or somebody else has this issue and you're unavailable, that they can understand what happened and how to fix it. And then the little things, quality posting, safety alerts. I like the idea of a display case, the bin of broken dreams, your failures, the hardware, the something that has failed, your crashed builds, your melted start plates, fun stuff that looks cool. I love having a display case. It's like, everybody's got the display case in the front of their shop of all the good parts they made. You can have the one in the back, too, that's all the accidents. Closing thoughts. Push the button. What's the worst that could happen? That's usually how I run, but don't allow your builds to be a fluke. Find out what happened. You run 3 builds, the second one failed. Don't just run a 4th one and just move. You can, sure, for the sake of time, but capture what happened. Figure out why that second one failed. Accountability is very important, but just assigning blame adds no value. And making those time cost-saving decisions absolutely increases risk of failure. So tread lightly on those. Let's see. I already talked about make sure you document everything as thoroughly as possible. Find corrective actions. When you find an error that something failed, put something in place so it doesn't happen again. It doesn't have to be bulletproof, but just to help that be prevented. And don't be afraid of failure. It happens to all of us. Again, back a slide, survey number 1 where people said 0. Maybe you've run 1 build and you've gotten lucky so far. I don't know. But with that, we can move to questions and answers.
Great. And we have quite a few questions, and we'll get to as many in the next 5 minutes as we can. All the way from Brazil, we have a question. Kudos from Sao Paulo. How much EMF caused fail events do you recall in your history? So how often do you have EMF caused fail events?
I don't know exactly what it was. I'm not sure we measured exactly what it was in the events I presented. But per the RKM manual, I believe it's plus or minus 2 milligauss variation. So as long as you stay within that window, and what we do is pretty much like I think a 3 or 5 meter circle around the electron gun, and anywhere within that circle, as long as you are staying within that plus or minus 2 milligauss, you should be good and not see any effects.
Okay, thank you. Question is, what is your typical process to determine the cause of visual defects?
Similar to what I was talking about with the, your specialized team, a lot of times that's what ends up happening. Sometimes it's very obvious. You can go through maybe your QM image files or your layer cam and look at the images and actually see what happened and say, oh, we short fed or it swelled up a little bit and popped above. But a lot of times it looks totally nominal in those pictures. And so that's where we've got the group of us that we've failed enough builds and we kind of know what's going on. And we have some discussions around it. And it ends up being a little bit of a team effort to really throw ideas out there and dive into it. But any evidence you can bring to the table really helps. Log files, like spitting those out and finding the Z height at which you've got that defect and using all those tools together to see if you can find something.
Okay. Question just came in. You mentioned like the hard and soft recoders, and the question is, could you please explain to us about the hard recoder crash problems?
Sure. So with concept laser machines, there are at least two different types of recoder blades. One is the rubber recoder, which is kind of like a windshield wiper material. And then there's the hard recoder. Typically like high-speed steel is the material. And the rubber one gives you a little bit of compliance. If you have any kind of swelling that your contours might be a little too hot and your part rises up a little bit above the focal plate after you've solidified it, or maybe you've got some internal stresses in the parts and they're bowing upwards ever so slightly that they start sticking up above the powder bed, the rubber blade will just ride right over the top of it and maybe not spread powder in those areas because they're so high up. Usually you'll see like a faint outline of the part if it's just starting to do that. But the hard recoder, if there's anything sticking up at all, it will, depending on the strength of your part that's being printed, usually jam. You run into the torque sensor on the recoder motor will reach its limit and that recoder has no deflection at all and just stops. Sometimes what we've experienced is actually we'll just shave the top of the part off. You're just sticking up a little bit, contours, it'll just skim that off and you'll end up with some metal shavings in the collector bin. So it can go either way.
All right, thank you. Next is, thanks for this good presentation. So would you say an AM-specific quality management system, for example, after ISO ASTM 52920, would help to reduce or even eliminate many different failures or problems that you encounter?
Yes, 100%. Absolutely. We are doing that here in our Cincinnati site for our print services group. We have now been, I believe we're AS 9100. We've at least been, I forget what the wording is for it, but suggested to apply for it or whatever. We've passed our audits. Absolutely. That's a huge chunk of, you've got your PM schedules, your control plans, for both process and design. All of these different things you put in place and plug them into some kind of, your ERP system that's controlling and scheduling. All of that comes together and definitely reduces failures. I don't think it is very difficult to get fail-free. I'd say that 90% of failures can be eliminated with 10% of the work, and the remaining 10% of failures take 90% of the work to remove from your system. But yes, a solid QMS is absolutely helpful.
Okay. How do you see in-process monitoring, for example, Sigma Labs, and AI taking a role in reducing build failure in the industry, both current and future?
I stay away from this because it's evolving so quickly. I can never seem to stay on top of what's the latest and greatest. I think the potential's there. I think there's a lot of still those unknowns and just the difference between simulation and what physically happens in the world that there's still just not quite perfect. I think the Internet of Things and simulations and in-process monitoring all combined can do an awesome job at resolving a lot of these failures. But I don't quite know yet. I've been out of that topic for quite a while now, so I'm not totally up to speed on it. But there's potential. I just don't think it's there yet.
Okay, we probably have time for one more quick question. Someone's asking about the Wednesday trash day example, which I think they just want to know, does that facility have a large backup UPS? Do you know?
I do not remember.
Okay. All right. So that,
Yeah, sorry.
yeah, if you don't know, that's going to conclude it. We have about 10 seconds left, and thank you all for joining us today. We hope you found this presentation valuable. This webinar will be available on demand if you'd like to listen to it again, or even pass it along to a friend or colleague. I also encourage you to register for upcoming webinars, which you can find on our website. You can also find pre-recorded webinars there. And finally, before you log off, we ask that you please complete our short survey that will pop up for you in a minute. Just share with us how your experience was today, and let us know of any other topics you'd like to hear about in the future. And we look forward to seeing you at our next webinar Wednesday. Thank you. Thanks, Dave.